Right now, somewhere on your phone, there's a blue dot. It sits on a map, and it knows where you are. If you pick up the phone and walk across the room, the dot moves. If you get in a car and drive across the city, the dot follows. It updates quietly, without fuss, and it's so reliable that you probably stopped thinking about it years ago. You open the map, the dot is there, and you trust it. You trust it to find the nearest gas station, to navigate an unfamiliar neighborhood at night, to tell a rideshare driver exactly where you're standing on a crowded street. But here's what's strange about that dot, and it's worth sitting with for a moment. Your phone doesn't actually know where it is. It has no built-in sense of location. There is no compass inside it that points to your street address, no sensor that reads the ground beneath your feet. What your phone does every few seconds is listen. It listens to faint radio signals arriving from satellites that are roughly 20,000 kilometers above your head, moving at nearly 4 kilometers per second, each one carrying a message that says almost nothing except the time. And from those timing messages, your phone performs a calculation. It measures how long each signal took to arrive, multiplies by the speed of light, and works out how far away each satellite must be. Then it does geometry. It finds the one point in space where all of those distances intersect, and it places the blue dot there. That's your location. Not a measurement of where you are, but a solution to a math problem that depends on the speed of light and the accuracy of atomic clocks orbiting the planet. The signal that carries this information arrives at your phone at roughly -130 decibels relative to a milliwatt. That is about 1,000 times weaker than the thermal noise your phone's own electronics generate. Your phone is fishing a whisper out of a room full of shouting. And yet the system works billions of times a day for billions of people on every continent. Tonight we're going to follow that signal from the satellite to your screen, through every layer of physics, engineering, mathematics, and history that makes it possible. We'll do it slowly because there is no rush, and because every layer turns out to be more interesting than the one above it. Let's start with what's actually up there, because the system begins 20,000 kilometers above the ground. The constellation of satellites that makes your blue dot possible is called the Global Positioning System, and it is operated by the United States Space Force. At any given moment, there are at least 24 operational GPS satellites in orbit, though the actual number is usually higher, because the Space Force maintains spare satellites that can be activated if an older one fails. As of recent counts, the constellation has included 31 or more operational satellites at various times. These satellites orbit in 6 distinct planes, each one tilted at about 55 degrees relative to the equator. The planes are spaced evenly around the Earth, 60 degrees apart from each other, so that together they wrap the planet in a lattice of coverage. The satellites within each plane are arranged so that from any point on the planet's surface, at any time of day or night, at least 4 satellites are visible above the horizon, usually more. In most places, at most times, your phone can see 7 or 8, sometimes more than a dozen. Each satellite circles the Earth twice every day, which means it completes one full orbit in approximately 12 hours. The orbital altitude, roughly 20,200 kilometers, is not arbitrary. It sits in what's called medium Earth orbit, and it was a carefully chosen compromise. Lower orbits would mean the satellites move across the sky faster, requiring more of them to maintain continuous coverage, and the signals would need to be more tightly focused. Higher orbits would spread the signals thinner and weaken them, and the geometry of the position calculation would become less favorable. The altitude they chose puts each satellite high enough to be visible from a wide area of the Earth's surface, covering roughly a third of the globe at any moment, but not so high that the signals weaken beyond what a small receiver can detect. To understand what medium Earth orbit means in physical terms, consider some reference points. The International Space Station orbits at about 400 kilometers. The geostationary communications satellites that relay television signals orbit at about 35,800 kilometers, high enough that their orbital period matches the Earth's rotation, and they appear to hang motionless in the sky. GPS satellites orbit between these two extremes, much higher than the space station, much lower than the geostationary ring. At 20,200 kilometers, each satellite moves at about 3.9 kilometers per second, fast enough that it crosses your visible sky in several hours. The satellites themselves are not small. A current generation GPS satellite, one of the Block 3 models built by Lockheed Martin, weighs roughly 2,200 kilograms and stretches about 5 meters across, with its solar panels deployed. It generates roughly 2,700 watts of electrical power, enough to run its transmitters and its onboard systems, drawing that power from the sun for most of each orbit. Each satellite spends about 45 minutes of every orbit in the Earth's shadow, during which time it runs on rechargeable batteries. The transition between sunlight and shadow, and back again, happens predictably, and the satellite's power system is designed to handle it without interruption. The satellites carry more than just the navigation payload. Each one has thrusters for maintaining its orbit, reaction wheels for controlling its orientation, thermal management systems for handling the extreme temperature swings between sunlight and shadow, and a command and control system that communicates with the ground stations. They also carry sensors that detect nuclear detonations, a secondary mission that dates back to the Cold War origins of the program. This nuclear detection capability is rarely mentioned in popular descriptions of GPS, but it's one of the reasons the military invested in the constellation in the first place. The design life of each satellite varies by generation. The earlier Block 2A satellites were built for a 7.5-year lifespan, though many exceeded that considerably. Some operated for more than 15 years before being decommissioned. The newer Block 3 satellites are designed for a 15-year operational life. When a satellite reaches the end of its useful life, whether from clock degradation, solar panel wear, thruster fuel depletion, or some other aging process, it is moved into a slightly higher disposal orbit to clear the operational slot, and a replacement is launched. The constellation is maintained like a living infrastructure, continuously replenished, with the oldest satellites being retired and the newest ones taking their place. The ground control segment monitors the health of every satellite continuously. If a satellite develops a clock anomaly, an unexpected orbit deviation, or any other condition that could degrade the accuracy of its navigation signal, the control segment can upload a health status warning that tells all receivers to ignore that satellite's signals until the problem is resolved. Receivers check these health flags automatically. If you're using GPS right now, your phone has already decided which satellites to trust and which to exclude, based on information it received from the satellites themselves. The constellation also has to contend with space weather. High-energy particles from solar flares can damage satellite electronics, cause bit flips in onboard memory, degrade solar panel efficiency, and create charging effects on the satellite's surface that can lead to electrostatic discharges. The satellites are radiation hardened to withstand most of this, but extreme events push the boundaries. During a major solar proton event, the ground control segment watches the satellite telemetry closely and may take protective actions, like rotating a satellite to reduce the exposed surface area, or switching to backup components if primary ones show signs of degradation. From the ground you can't see them. They're too far away and too small to spot with the naked eye, but they're there, all of them, circling in their 6 planes, each one broadcasting a signal toward the surface that says, in essence, here is the time, and here is where I am. That brings us to the clocks, because the entire system stands on them. Everything GPS does, every position it calculates, every route it guides you along, depends on measuring time with extraordinary precision, and the reason is a simple relationship that drives the whole architecture. Light travels at a fixed speed. In a vacuum, that speed is approximately 299,792,458 meters per second. Radio waves travel at the same speed because radio waves are light, just at a frequency your eyes can't detect. At that speed, light covers about 30 centimeters in 1 nanosecond. 1 nanosecond is 1 billionth of a second. To put that in perspective, 1 nanosecond is to 1 second as 1 second is to roughly 31.7 years. It is an almost inconceivably small amount of time. And yet it matters for GPS, because of that 30-centimeter relationship. If you want to know your position to within a meter, you need to know the time to within about 3 nanoseconds. If the clock is off by 10 nanoseconds, your position is off by 3 meters. If it's off by 100 nanoseconds, you're off by 30 meters. If it's off by a microsecond, a millionth of a second, which is 1,000 nanoseconds, your position is off by 300 meters. The precision of the clocks directly determines the precision of your location. This is why every GPS satellite carries atomic clocks, not ordinary quartz oscillators like the one in your wristwatch, but clocks that keep time by counting the natural vibrations of atoms. To understand what an atomic clock actually does, it helps to think about what timekeeping fundamentally is. Every clock works by counting something that repeats at a known rate. A pendulum clock counts swings. A quartz watch counts vibrations of a quartz crystal, which oscillates at a precise frequency when an electrical current is applied. An atomic clock counts something more fundamental still. It counts the oscillations of electromagnetic radiation emitted or absorbed by atoms, transitioning between specific energy levels. What makes atoms special as timekeepers is that every atom of a given element is identical. Every cesium-133 atom in the universe has exactly the same energy levels and produces exactly the same radiation frequency when it transitions between those levels. This frequency doesn't depend on temperature or pressure or where the atom is located or how the clock was manufactured. It's a property of the atom itself, fixed by the laws of physics. You can build 2 cesium clocks on opposite sides of the planet, and if they're working correctly, they will agree with each other to within fractions of a nanosecond per day. That's what makes atomic clocks the best timekeeping devices we have. The current GPS constellation uses 2 types of atomic clocks: rubidium clocks, which use the vibrations of rubidium atoms, and cesium clocks, which use cesium atoms. Newer satellites in the Block 3 generation also carry improved rubidium clocks that are more stable than the earlier versions. The cesium standard is particularly important because the international definition of the second itself is based on cesium. 1 second is defined as exactly 9,192,631,770 oscillations of the radiation produced by a cesium-133 atom transitioning between 2 specific energy levels. That is not a round number, and it was never meant to be. It is a physical constant, measured and agreed upon, and every atomic clock on every GPS satellite is ultimately calibrated against it. The rubidium clocks on the satellites are accurate to roughly 4 nanoseconds per day. That sounds impressive, and it is, but it's not accurate enough for the system to run unsupervised. A 4 nanosecond error translates to about 1.2 meters of position error, and that error accumulates. After a week, the clock would be off by about 28 nanoseconds, which is nearly 9 meters of position error. After a month, the drift would make the system noticeably less precise. So the clocks are monitored and corrected from the ground. The GPS ground control segment is a network of facilities spread around the world. At its core is the Master Control Station at Schriever Space Force Base in Colorado Springs, Colorado, with an alternate Master Control Station at Vandenberg Space Force Base in California. Supporting them is a network of monitoring stations located on every inhabited continent and on several remote islands, placed to give the control segment continuous visibility of every satellite in the constellation. Each monitoring station receives the GPS signals, measures the precise time at which each signal arrives, and forwards that data to the Master Control Station. By comparing measurements from multiple monitoring stations, the control segment can determine exactly how much each satellite's clock has drifted from the master timescale. It can also refine its knowledge of each satellite's actual orbital position, because the same timing measurements that reveal clock drift also reveal orbital deviations. The control segment then computes correction data and uploads it to each satellite through a network of ground antennas. These uploads happen typically twice a day, and they update the satellite's broadcast so that the navigation message carries the most accurate possible time and position information. The master timescale itself is maintained by the United States Naval Observatory, which operates an ensemble of highly precise atomic clocks on the ground. These ground clocks are even more accurate than the ones in space, and they serve as the reference against which the satellite clocks are measured and corrected. The Naval Observatory's timescale is called UTC, as maintained by the Naval Observatory, and it is one of several independent realizations of coordinated universal time, produced by national laboratories around the world. The whole system is, at its foundation, a timekeeping operation. GPS is a clock distribution network that happens to enable navigation. The satellites are flying clocks, broadcasting the time. Your phone is a clock comparator, measuring the difference between the satellite's time and its own, and the position comes out as a byproduct of that comparison. There is something worth pausing on here, because it connects the GPS clocks to one of the deepest questions in physics. The definition of the second, the one tied to cesium, was adopted in 1967 by the General Conference on Weights and Measures. Before that, the second was defined as a fraction of the mean solar day, which sounds natural, but turns out to be unreliable because the Earth's rotation is not constant. Tidal friction between the oceans and the seabed gradually slows the rotation, and irregular variations in the distribution of mass within the Earth cause unpredictable wobbles. An astronomically defined second drifts in ways you can't control. The cesium definition solved this by anchoring the second to something invariant. The transition frequency of cesium-133 is the same in every laboratory, on every continent, at every temperature. It doesn't change with the weather or the tides or the gravitational pull of the moon. By defining the second in terms of this transition, the international community effectively declared that time would no longer be measured by the motion of the Earth, but by the motion of atoms. It was a philosophical shift, as much as a practical one. The Earth is not a reliable clock, atoms are. This is the foundation GPS stands on. When the satellite clocks tick, they are counting something that is as close to universal and unchanging as physics provides. The precision of the position your phone calculates is a direct consequence of this decision, made decades before GPS existed, to define the basic unit of time in terms of atomic physics rather than astronomy. And the clocks are getting better. The next generation of atomic clocks being considered for space applications includes clocks based on optical transitions rather than microwave transitions. Optical clocks use transitions at much higher frequencies, hundreds of terahertz, rather than the roughly 9 gigahertz of cesium. Higher frequencies mean more oscillations per second to count, which means finer time resolution. Laboratory optical clocks have demonstrated stability and accuracy that exceed the best microwave clocks by orders of magnitude, losing or gaining less than 1 second in tens of billions of years. If optical clocks were eventually deployed on GPS satellites, the potential positioning accuracy would improve correspondingly. We are not there yet. The technology must be miniaturized, hardened against the space environment, and proven reliable over years of continuous operation. But the direction is clear. Better clocks mean better positions, and the clocks keep getting better. Now let's follow the signal itself, because the satellite has a clock, and it knows its own position, and it needs to tell your phone both of those things. The signal the satellite broadcasts is a radio wave. Like all radio waves, it travels at the speed of light. It is generated by the satellite's transmitter, amplified, and radiated toward the Earth through a shaped antenna that distributes the signal across the visible face of the planet. The antenna is designed to produce a cone of coverage wide enough that every point on the surface within the satellite's line of sight receives a usable signal. The signal carries 2 essential pieces of information. The first is the exact time, according to the satellite's clock, at the moment the signal was transmitted. The second is the satellite's ephemeris, a detailed mathematical description of where the satellite is in its orbit and where it will be for the next several hours. The ephemeris data is uploaded to the satellite by the ground control segment and updated regularly, to reflect the satellite's actual orbital path, corrected for the small perturbations caused by the gravitational pull of the Sun and Moon, the pressure of sunlight pushing against the satellite's body, and the slight drag of the residual atmosphere at that altitude. These forces are small, but over hours and days they add up, and if the satellite's broadcast position differs from its actual position, that difference becomes a position error for every user on the ground. GPS satellites broadcast on several frequencies. The original civilian signal, and still the most widely used, is broadcast on a frequency called L1 at 1575.42 MHz. This frequency was chosen partly because radio waves at this frequency can pass through the atmosphere with relatively low attenuation, and partly because it falls within a band that had been reserved for aeronautical radio navigation. A second civilian signal is broadcast on L2 at 1227.6 MHz, and a third, newer civilian signal is broadcast on L5 at 1176.45 MHz. Each frequency has slightly different characteristics. L5 was specifically designed for safety of life applications like aviation and carries a stronger signal with better resistance to interference. L2 provides a second frequency that allows dual-frequency receivers to measure and correct for ionospheric delay, which we'll get to later. Having multiple frequencies also provides redundancy. If interference or jamming affects one frequency, a receiver that tracks multiple frequencies has alternatives to fall back on. The data is encoded onto these carrier frequencies using a technique called spread spectrum, and understanding how it works is essential for understanding how GPS functions in the real world. The basic idea is this. The satellite takes its navigation data, which includes the timestamp and the ephemeris, and multiplies it by a pseudo-random noise code. This code is a long sequence of ones and zeros that looks like random static, but is actually a precisely defined pattern that repeats at a known interval. The code is called pseudo-random because while it appears random to anyone who doesn't know the pattern, it is entirely deterministic. Given the starting state and the algorithm, the sequence is predictable, which is essential because the receiver needs to generate an exact copy of it. Each satellite has its own unique pseudo-random noise code, assigned and documented in the GPS specifications. This is what allows your phone to distinguish signals from different satellites, even though they're all broadcasting on the same frequency at the same time. The technique is called code division multiple access. All the satellites share the same radio frequency, but each one uses a different code, and the codes are designed to be nearly uncorrelated with each other. When your phone multiplies the incoming signal by one satellite's code, the signals from all the other satellites average out to noise, while the target satellite's signal emerges from the background. The codes used for the standard civilian signal on L1 are called the coarse acquisition codes, and each one is 1023 bits long, repeating every millisecond. Each bit of the code is called a chip, and the chip rate is 1.023 million chips per second. This relatively short code makes initial signal acquisition fast, which is why it's called the coarse acquisition code. A receiver scanning for satellites can search through all possible code offsets in a reasonable amount of time. The military also uses longer, more precise codes called the P code, which chips at 10 times the rate of the civilian code. The P code, when encrypted, becomes the Y code, and together they form the PY code that gives military receivers their enhanced performance. But the civilian coarse acquisition code is what your phone uses, and its design is a masterpiece of signal engineering that balances acquisition speed against noise rejection. When your phone is searching for GPS signals, it generates a local copy of each satellite's code and slides it in time across the incoming radio energy, computing the correlation at each offset. When the local code aligns with the satellite's signal, the correlation peaks sharply, and the receiver knows it has found the signal and determined the time offset between the satellite's transmission and the receiver's local clock. This correlation process is what makes GPS work in the face of noise. The satellite signal is far weaker than the noise, but the known code acts as a matched filter, pulling the signal out of the background. Think of it this way. Imagine you're in a stadium full of people, and every person in the crowd is shouting random words at the same time. The noise is deafening, a wall of sound with no discernible pattern. But somewhere in that crowd, one person is reciting a specific poem that you know by heart. If you could somehow compare what you're hearing against the text of that poem, sliding your reference copy forward and backward in time until it aligns with the words embedded in the noise, the poem would emerge from the chaos and the rest of the shouting would cancel out. That is, roughly speaking, what your GPS receiver does with the pseudo-random codes. The noise is overwhelming, but the known pattern is detectable within it. It's like being at a loud party and hearing your own name called from across the room. The name is no louder than the surrounding conversation, but your brain is primed to detect that specific pattern, so it stands out. Your phone does the same thing with the pseudo-random codes. It knows what pattern to listen for, and even though the pattern arrives 1,000 times fainter than the noise, the correlation process makes it detectable. Once your phone has locked onto the signals from several satellites, it reads the timestamps and the ephemeris data from each one. The navigation message is encoded at a data rate of 50 bits per second, which means the information streams in slowly. The full navigation message, which includes clock correction coefficients, the satellite's precise orbital parameters, a health status word, ionospheric correction parameters, and an almanac describing the approximate orbits of all the other satellites in the constellation, takes 12.5 minutes to transmit completely. The data is organized into frames and subframes, with each subframe taking 6 seconds to deliver. The ephemeris data for the transmitting satellite is repeated in every frame, so a receiver doesn't need to wait for the full 12.5 minutes to compute a position fix. Once it has the ephemeris and the timestamps from 4 satellites, it can begin computing. And now your phone can do the central calculation that turns signals into position. The principle is called trilateration, and it is elegant in its simplicity. It's worth walking through carefully because the geometry is genuinely beautiful. To understand trilateration, it helps to start in 2 dimensions and then extend to 3. In 2 dimensions, if you know your distance from a single point, you know you're somewhere on a circle centered on that point. If you know your distance from 2 points, you're at one of the 2 places where the circles intersect. Add a third point, and in general, only one intersection remains. Now extend that reasoning into 3 dimensions. Imagine you're standing somewhere on the surface of the Earth and you know your exact distance from one satellite. That satellite is at a known point in space because its ephemeris told you where it is. Your distance from it describes a sphere centered on the satellite, and you are somewhere on the surface of that sphere. One satellite tells you that you are somewhere on a sphere. That's all. You could be at any point on that surface, which doesn't help much. Now add a second satellite. You know your distance from it too, so you're also on the surface of a second sphere. 2 spheres, unless one is entirely inside the other, intersect along a circle. So now you know you're somewhere on that circle. That's a dramatic narrowing. You've gone from the entire surface of a sphere to a single circle in space, but you still have infinitely many positions to choose from. Add a third satellite, 3 spheres, with 3 different centers and 3 different radii, generally intersect at exactly 2 points. Geometry guarantees this. 2 points, and usually one of them is out in space somewhere, far from the Earth's surface, while the other is near the surface, where a person could actually be standing. Your phone can discard the one that's obviously wrong and keep the one that's plausible. 3 satellites, 3 distances, 1 position. But there's a problem, and it's a fundamental one. To calculate your distance from a satellite, your phone needs to know how long the signal took to travel from the satellite to the receiver. It does this by comparing the timestamp in the signal, the moment the satellite says it transmitted the message, with the time on the phone's own clock when the message arrived. The difference between those 2 times is the signal's travel time, and multiplying by the speed of light gives the distance. Here's where the difficulty enters. Your phone's clock is not an atomic clock. It's a cheap quartz oscillator, accurate to maybe a few microseconds on a good day. And a microsecond of error in the clock means 300 meters of error in the distance calculation. That's not a small inaccuracy. That's placing you in the wrong neighborhood or the wrong part of a city. The error is consistent though. Whatever the offset between your phone's clock and the satellite clocks happens to be, it affects every distance measurement by the same amount. The distances your phone calculates are not true ranges but pseudo-ranges, ranges contaminated by a consistent clock bias. Every pseudo-range is off by the same number of meters, because the clock error adds the same number of nanoseconds to every travel time measurement. And this is where the fourth satellite becomes essential. Your phone has 4 unknowns to solve for. 3 of them are the coordinates of its position in space. You can think of these as latitude, longitude, and altitude, though the math actually works in 3-dimensional Cartesian coordinates, x, y, and z, relative to the center of the Earth. The fourth unknown is the error in the phone's own clock, the offset between the phone's quartz oscillator and the precise atomic time being broadcast by the satellites. 4 unknowns require 4 equations. Each satellite provides one equation, relating the measured pseudorange to the geometric distance between the satellite and the receiver, plus the unknown clock bias. The pseudorange from satellite 1 equals the true distance to satellite 1, plus the clock bias, times the speed of light. The pseudorange from satellite 2 equals the true distance to satellite 2, plus the same clock bias, times the speed of light. And so on for satellites 3 and 4. 4 equations, 4 unknowns. The system can be solved. This is a genuinely elegant piece of engineering. The system does not require your phone to have a precise clock. It uses the 4th satellite measurement to solve for the clock error as part of the position calculation. Every time your phone computes a GPS fix, it is also synchronizing its own clock to the atomic clocks in orbit, for free, as a byproduct of figuring out where it is. For a brief moment after each fix, your phone's internal clock is accurate to within nanoseconds of the satellite time, which makes it one of the most accurately timed devices in your possession. That accuracy fades quickly as the quartz oscillator drifts, but the next GPS fix resets it. The math behind the solution is a system of nonlinear equations, because the relationship between position and pseudorange involves square roots of sums of squared differences. The true distance from a satellite at known coordinates to a receiver at unknown coordinates is the Euclidean distance in 3 dimensions, which is the square root of the sum of the squared differences in x, y, and z. These square roots make the system nonlinear, which means it can't be solved by simple algebraic rearrangement. In practice, receivers use iterative numerical methods. They start with an approximate position, often the position from the last fix, and compute what the pseudo-ranges should be at that approximate position. They compare those predicted pseudo-ranges with the actual measured pseudo-ranges, compute the discrepancy, and use it to adjust the position estimate. After a few iterations, the solution converges, and the estimated position stabilizes. The process is fast enough to repeat several times per second, which is how your blue dot updates smoothly as you move. When more than 4 satellites are visible, which is almost always the case, the receiver has more equations than unknowns. This overdetermined system allows the receiver to apply least squares fitting or weighted statistical methods to find the best fit solution, and it can estimate the quality of that solution, producing a confidence measure that tells you how reliable the current fix is. More visible satellites generally mean a better fix, because the geometry improves and the effects of individual measurement errors are averaged across more independent observations. The geometry matters more than you might expect, and this is one of those details that reveals something about the nature of measurement itself. If all the visible satellites happen to be clustered together in one part of the sky, the position solution suffers. Imagine trying to determine your exact location by measuring your distance from 3 landmarks, but all 3 landmarks are in the same direction from you. The distance circles nearly overlap, and a small error in any one measurement produces a large shift in the calculated position. The same problem applies with GPS satellites. The best geometry has satellites spread evenly around the sky, high and low, north and south and east and west, providing lines of position that cross at wide angles. When the lines cross at wide angles, small measurement errors cause only small shifts in the solution. When the lines are nearly parallel, small errors cause large shifts. GPS receivers compute a number called the dilution of precision, which quantifies how the satellite geometry amplifies measurement errors into position errors. A dilution of precision value of 1 is ideal, meaning the geometry is as good as it can be and doesn't amplify errors at all. In practice, a value below 2 is considered excellent, and values up to 5 are acceptable for most consumer applications. Higher values mean the satellites are poorly distributed, and the position should be treated with caution. The dilution of precision is one of the factors your phone considers when deciding how much to trust the current GPS fix versus other positioning inputs. This brings us to one of the most remarkable aspects of the GPS system, and it involves physics that most people associate with theoretical science rather than everyday technology. The system would not work without correcting for the predictions of Albert Einstein's theories of relativity. Both of them, special relativity and general relativity, each affect the satellite clocks, and they do so in opposite directions. Let's take them one at a time. Special relativity describes how motion affects the passage of time. Einstein published the theory in 1905, and one of its central predictions is that a moving clock runs more slowly than a stationary clock. The faster the clock moves, the more slowly it ticks, relative to a clock at rest. This is not a mechanical effect caused by the motion jarring the clock's components. It is a fundamental property of time itself. Two observers moving relative to each other genuinely experience time at different rates. For everyday speeds, the effect is vanishingly small. A clock on an airplane flying at 900 kilometers per hour runs slower by roughly a few nanoseconds over a long flight. You would never notice. But GPS satellites move at roughly 3.9 kilometers per second, which is about 14,000 kilometers per hour. At that speed, special relativity predicts that the satellite clocks should tick more slowly than identical clocks on the ground, losing approximately 7 microseconds per day. 7 microseconds per day. At the GPS relationship of 30 centimeters per nanosecond, 7 microseconds is 7,000 nanoseconds, which corresponds to about 2.1 kilometers of position error per day from special relativity alone. Now consider general relativity. Einstein published the general theory of relativity in 1915, a decade after special relativity. General relativity describes how gravity affects the passage of time. A clock in a stronger gravitational field runs more slowly than a clock in a weaker gravitational field. Closer to a massive body, where gravity is stronger, time passes more slowly. Farther away, where gravity is weaker, time passes faster. GPS satellites orbit at 20,200 kilometers above the Earth's surface, where the gravitational field is weaker than it is at ground level. The satellites are farther from the center of the Earth than you are, so they experience less gravity. General relativity predicts that the satellite clocks should tick faster than ground clocks, gaining approximately 45 microseconds per day. The two effects work in opposite directions. Special relativity slows the satellite clocks by about 7 microseconds per day because of their orbital speed. General relativity speeds them up by about 45 microseconds per day because of their higher altitude and weaker gravity. The net effect is that the satellite clocks run fast by approximately 38 microseconds per day compared to clocks on the ground. 38 microseconds might not sound like much, but 38 microseconds is 38,000 nanoseconds. At 30 centimeters per nanosecond, that's about 11.4 kilometers of position error per day. If the system did not correct for relativity, your blue dot would drift by more than 10 kilometers every single day. After a week, it would be off by nearly 80 kilometers. GPS would be useless for navigation within hours of being turned on. The correction is built into the hardware before the satellite ever leaves the ground. Each satellite's onboard clocks are deliberately set to tick at a slightly different frequency than they would at the Earth's surface. The adjustment is tiny, a shift of about -4.467 parts in 10 billion applied to the fundamental frequency of the clock. This means that on the ground, before launch, the clock actually ticks at the wrong rate. But once the satellite reaches its operational orbit and the relativistic effects take hold, the pre-adjusted clock ticks at precisely the correct rate as observed from the Earth's surface. This is one of the most direct and practical applications of Einstein's theories in everyday life. Every time your phone places the blue dot on the map, it is relying on corrections derived from general and special relativity. The physics of curved spacetime is engineered into the satellite hardware, running silently in the background every second of every day. If you removed the correction, you would notice within minutes. Neil Ashby, a physicist at the University of Colorado, published a thorough analysis of the relativistic effects in GPS in a paper for the journal Living Reviews in Relativity. Ashby's treatment covered not only the primary effects of special and general relativity, but also subtler contributions, including the Sagnac effect, which arises because the Earth is rotating and the signal paths between satellites and receivers curve through a rotating reference frame. He also addressed the eccentricity of the satellite orbits, because GPS orbits are not perfectly circular and the altitude varies slightly over each orbit, causing the relativistic correction to oscillate over the course of a day. The receiver must account for this oscillation in real time. Ashby's work became one of the standard references for understanding how relativity enters the GPS calculation, and it showed that the corrections are not approximate estimates. They are precise, quantitative, and essential for meter-level accuracy. There is a story, possibly apocryphal but widely repeated in the GPS engineering community, that when the relativistic corrections were first proposed during the system's development in the 1970s, some engineers were skeptical. They doubted that the effects would be large enough to matter for a navigation system. The system's designers reportedly built in the ability to activate or deactivate the relativistic correction so that the effect could be measured directly once the satellites were in orbit. When the first satellites were launched and the data came in, the measurements confirmed Einstein's predictions precisely. The correction was necessary, and it was accurate. It has been running continuously ever since. There is a secondary relativistic effect worth mentioning, because it illustrates how subtle the physics becomes when you demand nanosecond precision. GPS satellite orbits are not perfectly circular. They are slightly elliptical, with eccentricities typically around 0.01. This means the satellite's altitude varies slightly over the course of each orbit, rising a few dozen kilometers at apogee and falling a similar amount at perigee. As the altitude changes, so does the gravitational time dilation. At higher altitude, the clock runs slightly faster. At lower altitude, slightly slower. The oscillation is small, but at GPS precision levels, it is measurable. This periodic effect is called the eccentricity correction, and it must be computed by the receiver in real time. The receiver knows the satellite's orbital parameters from the ephemeris data, so it can calculate where the satellite is in its orbit at any given moment and apply the corresponding correction. The magnitude of the eccentricity correction depends on the satellite's particular orbit and can amount to tens of nanoseconds over the course of an orbit. That's meters of range error if left uncorrected. There is also the Sagnac effect, which arises because the Earth is rotating. While a GPS signal is in transit from the satellite to the receiver, the Earth rotates underneath it. The receiver moves. If the signal is traveling in the same direction as the Earth's rotation, the path length is effectively shorter because the receiver is rotating toward the signal. If the signal is traveling against the rotation, the path is longer. The Sagnac correction adjusts for this rotation, and it can amount to to roughly 100 nanoseconds for a signal crossing the full diameter of the Earth's surface. For most fixes, where the satellites are at various angles, the correction is smaller, but still significant, at the nanosecond level. Now, even with perfectly corrected satellite clocks and precise orbit information, the position your phone calculates is still an estimate, because several sources of error affect the signal on its way from the satellite to your receiver. Understanding these error sources is important because they determine the practical accuracy of the system, and each one has been the subject of decades of engineering effort to reduce or correct. The largest single source of error for civilian users is the ionosphere. The ionosphere is a region of the Earth's upper atmosphere that extends from roughly 60 kilometers above the surface to more than 1,000 kilometers in altitude. At these heights, solar radiation strips electrons from atmospheric atoms, creating a diffuse plasma of free electrons and ions. The density of this plasma varies with the time of day, the season, the solar cycle, and the latitude. During the day, when the sun is pouring energy into the atmosphere, the ionization is denser. At night, it thins. During periods of high solar activity, the ionosphere can become significantly more dense and more variable. When a GPS signal passes through this layer of charged particles, the signal slows down. The electromagnetic wave interacts with the free electrons, and the effect is to reduce the signal's group velocity below the speed of light in a vacuum. The signal takes slightly longer to reach the receiver than it would if it were traveling through empty space. The receiver, which assumes the signal traveled at the speed of light, calculates a distance that is slightly too large. This shows up as a position error. The physics of this interaction is worth exploring a bit further. When a radio wave enters a plasma, the free electrons in the plasma oscillate in response to the wave's electric field. These oscillating electrons radiate their own electromagnetic waves, which interfere with the original wave. The net effect is to change the wave's apparent velocity. For GPS frequencies, the effect is to slow the group velocity, the speed at which the signal's information content travels, while actually increasing the phase velocity, the speed at which the wave crests move. This is counterintuitive but well understood. The group delay is what matters for pseudorange measurements, and it causes the receiver to overestimate the distance to the satellite. The total electron content along the signal path, the integrated number of free electrons per square meter in a column from the satellite to the receiver, determines the magnitude of the delay. This quantity varies enormously. It depends on the sun's position relative to the signal path, on the latitude, on the season, on the phase of the 11-year solar cycle, and on transient events like solar flares and coronal mass ejections that can dump enormous amounts of energy into the upper atmosphere on timescales of hours. The magnitude of the delay depends on the density of the ionization along the signal's path and on the frequency of the signal. The delay is inversely proportional to the square of the frequency, which means lower frequencies are delayed more than higher frequencies. On a quiet day, the ionospheric delay might add a position error of a few meters. During a geomagnetic storm, when solar activity disturbs the ionosphere significantly, the error can grow to tens of meters. This frequency dependence is precisely why GPS uses multiple frequencies. A receiver that can track the same satellite signal on two different frequencies can measure the difference in delay between them. Because the ionospheric delay varies with frequency in a known mathematical relationship, the receiver can use the measured difference to calculate the actual ionospheric delay and remove it from the pseudorange measurement. Dual-frequency receivers achieve significantly better accuracy than single-frequency receivers because of this correction. Most consumer devices, including most smartphones, historically used only the L1 frequency and relied on a mathematical model of the ionosphere to estimate the delay. The model, called the Klobuchar model after its designer, uses parameters broadcast in the GPS navigation message that describe the current state of the ionosphere in broad terms. The model corrects for roughly half to two-thirds of the ionospheric error, which is helpful but imperfect. In recent years, some high-end smartphones have begun including dual-frequency GPS chips, that can track both L1 and L5, providing much better ionospheric correction and improving accuracy to roughly 3 meters under favorable conditions. Below the ionosphere, the signal passes through the troposphere, the lowest layer of the atmosphere. The troposphere extends from the surface to roughly 12 kilometers in altitude and contains the air you breathe, the weather you experience, and the water vapor that drives many atmospheric processes. The troposphere also delays GPS signals, but for a completely different physical reason than the ionosphere. The tropospheric delay is caused by the refractivity of the air itself, which depends on its temperature, pressure, and humidity. The delay has two components. The dry component, caused by the nitrogen and oxygen in the atmosphere, accounts for about 90% of the tropospheric delay and is well modeled using standard atmospheric pressure data. The wet component, caused by water vapor, is more variable and harder to predict because the distribution of moisture in the atmosphere changes rapidly. The total tropospheric delay adds roughly 2 to 3 meters of equivalent range error for a satellite directly overhead. For satellites near the horizon, where the signal passes through a longer path of atmosphere, the delay can be several times larger. Receivers estimate the tropospheric correction using atmospheric models and the known elevation angle of each satellite, and the correction is generally adequate for consumer-level accuracy. Unlike the ionospheric delay, the tropospheric delay affects all frequencies equally, so multiple frequency receivers cannot use the frequency comparison technique to correct it. The troposphere is a fundamentally different kind of challenge than the ionosphere. Another significant source of error is multipath. Multipath occurs when a GPS signal bounces off a nearby surface, a building, a mountain, a body of water, the ground itself, before reaching the receiver. The reflected signal travels a longer path than the direct signal, so it arrives at the receiver slightly later. If the receiver processes the reflected signal alongside the direct signal or mistakes the reflected signal for the direct one, the pseudorange measurement is contaminated by the extra path length. Multipath is worst in urban environments. When you're walking between tall buildings, GPS signals bounce off glass facades, concrete walls, and metal structures from multiple directions. The receiver may see several copies of each satellite signal arriving at slightly different times, and sorting out the direct signal from the reflections is a significant signal processing challenge. This is one of the main reasons your blue dot sometimes jumps erratically when you're in a dense downtown area. The receiver is struggling with multipath, and the position solution bounces around as the multipath environment changes with each step you take. Modern receivers use various techniques to mitigate multipath. They can compare the shape of the correlation peak to the ideal shape expected for a direct signal, rejecting peaks that show the characteristic distortions caused by reflected signals. They can use multiple antennas and compare the signals received at each one. And they can use advanced signal processing algorithms that model the multipath environment and attempt to extract the direct signal from the contaminated measurement. These techniques help, but multipath remains one of the hardest error sources to eliminate completely, especially in consumer devices with small antennas and limited processing power. Then there is orbital error, the difference between the satellite's actual position at the moment of signal transmission and the position predicted by the ephemeris data in the navigation message. The ground control segment tracks each satellite and updates its orbital parameters regularly, but between updates, gravitational perturbations, solar radiation pressure, and other forces cause the satellite to deviate slightly from the predicted path. The resulting position error is typically small, a meter or two, but it contributes to the overall uncertainty in the fix. There is also a subtle error source called the satellite antenna phase center offset. The GPS signal is not radiated from a mathematical point, but from a physical antenna that has a finite size. The effective origin of the signal, the phase center, may not coincide precisely with the geometric center of the satellite that the ephemeris describes. The offset between these 2 points, which can amount to a few centimeters, must be modeled and corrected for in high-precision applications. For consumer receivers, this error is small enough to be absorbed into the overall noise, but for surveying and geodetic work, it matters. Similarly, the receiver antenna has its own phase center variation. As the elevation and azimuth of the satellite change, the effective point at which the antenna receives the signal shifts slightly. High-precision receivers use calibrated antenna models that account for this variation as a function of the signal direction. Consumer devices do not, which is another source of the accuracy gap between a phone and a survey instrument. And there is receiver noise, the inherent imprecision in the receiver's measurement of signal arrival time. Every electronic measurement has a noise floor determined by the quality of the components, the design of the circuits, and the ambient electromagnetic environment. In a dedicated survey-grade GPS receiver, with a large antenna, a low-noise amplifier, and careful circuit design, the receiver noise is minimized. In a phone, where the GPS chip shares silicon and board space with a cellular radio, a Wi-Fi transceiver, Bluetooth, near-field communication, and a dozen other subsystems, each one generating its own electronic noise, the measurement precision is inherently coarser. When you add all of these error sources together, a consumer GPS receiver typically achieves a horizontal position accuracy of somewhere between 3 and 15 meters under open sky, with a reasonable satellite geometry. In a dense urban canyon, accuracy can degrade to 20 meters or more. In a wide open field with a clear view of the sky, good satellite geometry, and favorable atmospheric conditions, it can be as good as 2 to 3 meters. The number your phone displays as a position is always the best estimate it can produce from imperfect measurements, and the quality of that estimate varies from second to second as the satellite geometry shifts, the atmospheric conditions change, and the local multipath environment evolves. There are systems designed to improve that estimate, and they work by removing error sources that the receiver alone cannot correct for. The most important one for civilian users in North America is the Wide Area Augmentation System, commonly called WAAS, operated by the Federal Aviation Administration. WAAS was designed primarily for aviation, to provide the kind of accuracy and integrity guarantees that aircraft need for instrument approaches and landings, but it is freely available to any receiver that supports it, and many consumer GPS devices and smartphones use WAAS corrections automatically when they are available. The system works like this. The FAA maintains a network of precisely surveyed reference stations across North America. There are roughly 36 of them, distributed from Alaska to the Caribbean. Each station receives the GPS signals and, because it knows its own exact position to within centimeters, can calculate the errors in those signals at its location. The errors include ionospheric delay, satellite clock drift, and satellite orbit errors. All of these can be measured by comparing what the station receives with what it knows should be true. The error measurements from all the reference stations are collected and sent to master stations, where they are analyzed and combined into correction messages. These messages are then uplinked to geostationary satellites, 2 of them covering North America, which broadcast the corrections back down to the surface on the same L1 frequency that GPS uses. Any WAAS-capable receiver can pick up these correction broadcasts and apply them to its GPS measurements. The corrections are specific to the receiver's region and the current atmospheric conditions, so they provide meaningful improvements tailored to the user's actual situation. With WAAS corrections applied, civilian GPS accuracy improves from roughly 10 to 15 meters down to approximately 3 to 5 meters in most conditions. For aviation, where GPS is increasingly used for precision approach and landing guidance, this improvement, combined with the integrity monitoring that WAAS provides, allows aircraft to safely descend to lower altitudes before deciding whether to land or go around. The integrity monitoring is arguably more important than the accuracy improvement for aviation. It tells the pilot's instruments whether the GPS data can be trusted at this moment, which is a question that matters more when you're 200 feet above the runway than when you're finding a coffee shop. Similar systems operate in other regions of the world. Europe operates the European Geostationary Navigation Overlay Service. India operates GPS-aided geo-augmented navigation. Japan operates the multifunctional satellite augmentation system. Each one uses the same basic approach: ground reference stations measuring GPS errors, master stations computing corrections, and geostationary satellites broadcasting those corrections to users in the coverage area. Beyond satellite-based augmentation, there are ground-based systems that push accuracy even further. Differential GPS uses a single reference station, typically within a few tens of kilometers of the user, to compute corrections in real time. Because the reference station and the user's receiver are geographically close, they experience nearly the same ionospheric and tropospheric delays, and their pseudorange errors are strongly correlated. The corrections from the nearby reference station can remove most of the atmospheric errors, along with satellite clock and orbit errors. With a good differential GPS setup, accuracy can reach sub-meter levels, routinely achieving positions accurate to within 30 to 50 centimeters. And at the extreme end of GPS precision, there is a technique called real-time kinematic positioning, known as RTK. RTK represents a fundamentally different approach to GPS measurement. Instead of using the pseudo-random codes to measure signal arrival time, RTK uses carrier phase measurements. It tracks the actual wave cycles of the GPS carrier frequency, counting the number of complete oscillation cycles between the satellite and the receiver. The L1 carrier frequency oscillates at 1575.42 MHz, which means each complete wavelength is about 19 centimeters long. By counting these wavelengths and measuring the fraction of a wavelength at the receiver, the system can determine the distance to the satellite with a resolution far finer than the code-based measurement allows. The challenge is resolving the integer ambiguity, figuring out how many complete wavelengths fit in the total distance, because the measurement only directly gives you the fractional part. This is a difficult mathematical problem, but modern algorithms can solve it reliably, using signals from multiple satellites on multiple frequencies. When RTK combines these carrier phase measurements with real-time corrections from a nearby base station, typically within 20 or 30 kilometers, it achieves centimeter-level accuracy, 2 centimeters horizontally. This is the technology that allows a self-driving tractor to plant rows of seeds with centimeter precision, a surveyor to place boundary markers accurate to within 2 centimeters, or a construction crew to grade a road surface to its designed profile. RTK requires specialized equipment and a nearby base station, and it costs substantially more than a consumer GPS receiver, but it demonstrates just how precise the underlying physics can be when the error sources are carefully controlled. All of these augmentation techniques build on the foundation of the basic GPS signal. They do not replace the satellites or the timing. They refine the measurement by reducing the errors that the basic system cannot eliminate on its own. The signal is always the starting point. The corrections make it better. Now let's go back in time, because the system that places your blue dot today didn't appear fully formed. It was built over decades by people solving problems that nobody else thought were solvable, and it emerged from the convergence of 3 separate programs that were each trying to do something slightly different. The idea of using satellites for navigation is about as old as the space age itself. Within months of the launch of Sputnik in October of 1957, researchers at the Applied Physics Laboratory at Johns Hopkins University noticed that they could track Sputnik's orbit by measuring the Doppler shift of its radio signal. The signal's frequency shifted predictably as the satellite approached and then receded, rising as it came closer and falling as it moved away. From the rate and pattern of that shift, they could determine the satellite's orbit. The researchers, William Geyer and George Weifenbach, were not assigned to track the satellite. They did it on their own initiative, out of curiosity, using the lab's equipment. The fact that 2 physicists working on their own time could determine a satellite's orbit from a single ground station using nothing but frequency measurements was a remarkable demonstration, and it led them to a realization that would change the world. They quickly realized the inverse was also true. If you already knew the orbit of the satellite, You could use the same Doppler measurements to determine the position of the receiver on the ground. This insight became the basis for the first satellite navigation system. The United States Navy, which needed a way to precisely locate its ballistic missile submarines for accurate weapons targeting, funded the development of a system based on this principle. The result was Transit, also known as the Navy Navigation Satellite System. Transit launched its first experimental satellite in 1960, and the system became operational for the Navy in 1964. Transit worked, but it had significant limitations. Each position fix required tracking a single satellite as it passed overhead, measuring the Doppler shift of its signal for about 15 minutes as it crossed the sky. Fixes were only available when a satellite happened to be passing, and with a constellation of only 5 or 6 operational satellites, there were gaps of an hour or more between passes when no navigation was available. The accuracy was modest, typically a few hundred meters, and the fix gave only a two-dimensional position, latitude and longitude, not altitude. The user also had to be stationary, or nearly so, during the 15-minute observation period. For a submarine that surfaced briefly to get a fix before submerging again, Transit was adequate. For a vehicle or an aircraft that needed continuous real-time positioning, it was not. Transit worked well enough that it became the standard navigation system for the Navy's Polaris submarine fleet. A submarine would surface, extend its antenna, receive a transit pass, compute a fix, and submerge again. The fix allowed the submarine's inertial navigation system to be recalibrated, resetting the accumulated drift. For a ballistic missile submarine, the precision of the position fix directly affects the accuracy of the missiles it carries. A navigation error in the submarine's position becomes a targeting error in the missile's flight path. Transit's accuracy, while modest by modern standards, was a significant improvement over the purely celestial and inertial methods that had been available before. Beyond the military, Transit was opened to civilian use in 1967 and found a dedicated following among commercial mariners, particularly in the fishing and surveying industries. Geodesists used it to establish precise survey control points around the world, taking advantage of the fact that many repeated fixes from the same location could be averaged to produce positions accurate to within meters, far better than any single pass could achieve. Transit continued to operate until 1996, outlasting even its designers' expectations, but its limitations drove the search for something better, and the search produced 3 separate approaches. At the Naval Research Laboratory in Washington, a physicist and inventor named Roger Easton was working on a concept he called timation. Easton's central insight was that precise timekeeping was the key to accurate satellite navigation. If you could put extremely accurate clocks on satellites and synchronize them carefully with clocks on the ground, you could use the time of arrival of the satellite signals to calculate distances, one satellite at a time, and combine those distances to determine position. Easton's approach was different from Transit in a fundamental way. Transit used Doppler shift, which measures velocity, and derived position from the accumulated velocity data. Timation used timing, which measures distance directly. The distinction matters because a timing-based system can produce an instantaneous position fix from simultaneous measurements of multiple satellites, while a Doppler-based system needs an extended observation period. Easton's timation program launched its first test satellite in 1967. It carried a quartz crystal oscillator and demonstrated that timing-based ranging from space was feasible. A second timation satellite launched in 1969, also with a quartz clock, but with improved stability. And a third satellite, launched in 1974, carried something that had never been flown in space before, a rubidium atomic clock. That satellite demonstrated that an atomic clock could operate reliably in the orbital environment, surviving the vibration of launch, the vacuum and radiation of space, and the thermal cycling between sunlight and shadow. Easton's work proved the timing foundation on which the entire GPS concept would eventually rest. Meanwhile, at the Air Force, a separate program called Project 621B was exploring another approach. This program used ranging signals exchanged between a satellite and a ground receiver to measure distance, similar in concept to what Timation was doing, but using different signal architectures and a different constellation design. The 621B system required the receiver to transmit as well as receive, which had two disadvantages. It made the equipment larger and more power-hungry, and it revealed the user's position to anyone who could detect the transmission. For a military system, the fact that using the navigation system betrayed your location was a serious problem. By the early 1970s, 3 satellite navigation concepts existed within the Department of Defense. Transit was operational but slow, intermittent, and limited in accuracy. Timation had demonstrated timing-based positioning with atomic clocks and passive receivers, and Project 621B had explored ranging techniques for 3-dimensional positioning but required the user to transmit. Each program was managed by a different service branch. Each had its own champions and its own institutional momentum, and none of them alone provided what the military actually needed: continuous, worldwide, 3-dimensional, all-weather positioning with passive receivers that didn't reveal the user's location. In September of 1973, a meeting at the Pentagon brought together representatives from all 3 programs. The meeting was organized by the Office of the Deputy Secretary of Defense, and it was the moment where the synthesis happened. Chaired by a colonel named Bradford Parkinson, an Air Force officer with a background in inertial navigation and satellite engineering, the meeting produced the design concept that would become GPS. Parkinson had been assigned by the Air Force to lead the Joint Program Office for a new satellite navigation system, and he arrived at the September meeting with a clear vision of what the system should look like. He wanted a constellation of satellites broadcasting one-way signals so the receiver could be completely passive. He wanted the signals to carry precise timing from atomic clocks so the receiver could compute distances from signal arrival times. He wanted enough satellites to provide continuous worldwide coverage, with at least 4 visible from any point at any time. And he wanted the system to provide 3-dimensional positioning plus velocity. The resulting design took the best elements from each predecessor program. From transit, it inherited the concept of a satellite constellation, operated by the military for global coverage. From Timation, it took the principle of precise timekeeping as the basis for ranging, along with the demonstrated use of atomic clocks in space. The timing concept was the heart of the system. From Project 621B, it adopted the goal of 3-dimensional positioning and the signal structures that enabled it. But critically, the new design was passive. Unlike 621B, the receiver did not need to transmit. It only listened to the satellite signals and computed its position locally. This meant the receiver could be small, inexpensive, and completely silent, revealing nothing about the user's location. The system was given the name Navstar, an acronym for Navigation Signal Timing and Ranging, though it became universally known simply as GPS. The formal approval came in December of 1973, when the Defense Systems Acquisition Review Council authorized the concept validation phase. The program was assigned to the Air Force Space and Missile Systems Organization in Los Angeles, and Parkinson was named its first director. The early years were marked by technical challenges and budgetary battles in roughly equal measure. The satellite design had to accommodate atomic clocks that had never operated in orbit, transmitters that had to broadcast signals powerful enough to be received on the ground, but efficient enough to run on limited solar power, and an orbit high enough to provide wide coverage, but low enough to keep the signals detectable. Every design choice involved trade-offs, and the team had to navigate competing requirements from the Army, Navy, Air Force, and Marine Corps, each of which had different priorities for what the system should optimize. Bradford Parkinson led the program through its earliest and most difficult years. He fought bureaucratic battles with multiple branches of the military, each of which wanted the system optimized for its own needs. The Air Force wanted it for aircraft navigation and precision weapons delivery. The Navy wanted it for submarine positioning. The Army wanted portable receivers for ground troops. Parkinson argued for a universal system that served all of them, and he prevailed, though not without opposition. There were moments when the program came close to being cancelled or reduced in scope, and Parkinson's persistence in defending its vision was critical to its survival. But GPS did not have a single inventor. Roger Easton's work on timation provided the timing foundation, without which the concept is meaningless. Ivan Getting, who had been president of the Aerospace Corporation since 1960, had been advocating for a satellite-based positioning system since the early 1960s. Getting helped shape the requirements and the institutional framework that made the program possible. His contributions were organizational and conceptual, working at the level of defense policy and systems architecture rather than satellite hardware. He articulated the need for a three-dimensional, all-weather, continuous positioning system years before the technology existed to build one. The first experimental GPS satellite, designated Navstar 1, was launched on February 22, 1978, from Vandenberg Air Force Base in California, aboard an Atlas F rocket. It carried rubidium and cesium atomic clocks and began broadcasting the signals that would eventually guide your phone. The satellite operated until 1985, well beyond its design life. More satellites followed over the next several years. The experimental Block 1 satellites, 11 of them launched between 1978 and 1985, demonstrated that the concept worked. They validated the signal structure, the timing approach, the orbital mechanics, and the receiver technology. They showed that a passive receiver on the ground could track signals from multiple satellites simultaneously and compute a three-dimensional position in real time. The Block 1 satellites were followed by the Block 2 production satellites, the first fully operational constellation. Block 2 satellites, along with their improved variants Block 2A, Block 2R, Block 2RM, and Block 2F, populated the 6 orbital planes and brought the system to full worldwide coverage. Each generation brought improvements, better clock accuracy, additional signal frequencies, increased resistance to jamming, and longer design lifetimes. The Block 2R satellites, for example, had the ability to generate their own navigation messages autonomously, allowing the constellation to function for weeks without ground intervention if the control segment were disrupted. The GPS system was declared fully operational in April of 1995, 17 years after the first satellite launch, and 22 years after the synthesis meeting at the Pentagon. By that time, the constellation had reached its designed configuration of 24 satellites in 6 orbital planes, providing continuous worldwide coverage. Any receiver, anywhere on Earth, at any time, could compute a three-dimensional position fix using only the freely broadcast signals. But the path from military experiment to the civilian utility you use today was not smooth. It was shaped by a tragedy. On September 1, 1983, Korean Airlines Flight 007, a Boeing 747 carrying 269 people from New York City to Seoul by way of Anchorage, strayed into Soviet airspace while crossing the North Pacific. The aircraft had deviated from its planned route, drifting over the Kamchatka Peninsula and then over Sakhalin Island, both of which were militarily sensitive Soviet territory. Soviet interceptors tracked the aircraft for hours. After it failed to respond to interception procedures, a Sukhoi Su-15 fighter launched 2 air-to-air missiles. The aircraft was hit and crashed into the Sea of Japan. Everyone on board was killed. The incident shocked the world. 269 people, including a sitting United States Congressman, Larry McDonald of Georgia, were dead. The Soviet Union initially denied shooting down the aircraft, then claimed it had been on a spy mission. The black boxes were never recovered during the initial search, though the Soviet Navy had secretly retrieved them. The full cockpit voice recorder and flight data recorder were not made public until the Soviet Union dissolved years later. The incident provoked an international crisis. The investigation focused heavily on how the aircraft had gone so far off course. The most likely explanation was an error in the inertial navigation system. The Boeing 747 of that era used inertial navigation for transoceanic flights, a self-contained system that measured accelerations and integrated them over time to track position. Inertial navigation works without external signals, which is its strength, but it accumulates errors over long flights, which is its weakness. A mistyped waypoint or an incorrect initial position entry can compound over hours into a deviation of hundreds of kilometers. The navigational error was heartbreaking in its banality. The crew had multiple navigation systems available, including the inertial units and a VHF omnidirectional range station they could have tuned to verify their position. But the inertial system, once initialized with the wrong mode or a stale position, would quietly propagate the error, showing the crew a path that looked correct on their instruments but was hundreds of kilometers from reality. The system didn't fail in any obvious way. It simply told the crew they were somewhere they weren't, and they had no reason to doubt it. That is the most dangerous kind of navigation error, the kind that feels like no error at all. 2 weeks after the shootdown, President Ronald Reagan made an announcement that would reshape the future of navigation. He declared that the global positioning system, which was still under development and intended primarily for military use, would be made available to civilian users free of charge, worldwide, once the system was fully operational. The stated rationale was to prevent navigational tragedies like the one that had befallen Flight 007. If civilian aircraft had access to satellite navigation, the reasoning went, the kinds of navigational errors that led to the shootdown would become far less likely. Reagan's announcement did not immediately open GPS to full civilian use. The system was not yet operational, and the details of the civilian service still needed to be worked out, but it set the policy direction that persists to this day. GPS would be a dual-use technology, serving both military and civilian needs, and the civilian signal would be broadcast freely, to anyone with a receiver, anywhere in the world, with no subscription fee, no usage charge, and no requirement to register or identify yourself. There was a catch, however, and it was a deliberate one. From the beginning, the military was concerned that adversaries could use the same precise GPS signals to guide their own weapons, so the civilian signal was intentionally degraded through a feature called selective availability. Selective availability worked by introducing deliberate errors into the civilian GPS signal. The satellite's broadcast timing data was slightly altered in a controlled but unpredictable way, adding a random wobble to the pseudo-range measurements that civilian receivers computed. With selective availability active, civilian receivers could determine their position to within about 100 meters. The military receivers, which used a separate encrypted signal immune to selective availability, could achieve accuracy of roughly 10 to 20 meters. 100 meters is good enough to know which part of a city you're in, but it's not good enough to navigate a car through an intersection, find a specific building on a long street, or guide any precision operation. For years, civilian GPS was useful but imprecise, and the imprecision was not a technical limitation of the system. It was a policy choice, an intentional degradation applied to the civilian signal by the same government that broadcast it. The end of selective availability came on May 1, 2000. President Bill Clinton directed that the feature be turned off, effective immediately. At midnight, the deliberate errors were removed from the civilian signal. Overnight, civilian GPS accuracy improved from roughly 100 meters to roughly 20 meters. The improvement was dramatic and instantly noticeable to anyone with a GPS receiver. Clinton's order was accompanied by a statement that the United States had no intent to use selective availability again. The decision was driven by several factors. The deliberately degraded civilian signal was hurting American commercial interests, making GPS less competitive against other positioning technologies and slowing the development of civilian applications. Differential GPS techniques had already been developed that could cancel out the selective availability errors, so the degradation was becoming less effective as a military advantage, and the military had developed the ability to deny GPS selectively in specific regions during conflict, through localized jamming, rather than degrading the signal globally. The blunt instrument of selective availability was no longer needed. The technical mechanism of selective availability is worth understanding because it reveals the deliberateness of the degradation. The system worked by dithering the satellite clock data in the navigation message, adding a slowly varying error to the broadcast clock corrections. This made the pseudorange measurements computed by civilian receivers fluctuate unpredictably. The error pattern was controlled by a classified algorithm, changed regularly, and known only to the military. The dithering was called epsilon, and a separate component called delta manipulated the broadcast ephemeris data. Together, these two perturbations degraded the civilian solution to about 100 meters of horizontal accuracy, 95% of the time. The military's encrypted PY code signal was immune to both because military receivers used a different set of clock and ephemeris corrections that were not subject to the dithering. The removal of selective availability was a turning point. It made GPS accurate enough for the applications that now define how most people use it. Turn-by-turn car navigation, ride-hailing services that match drivers with passengers, geotagged photographs, location-based search results, fitness tracking, precision agriculture, drone navigation, augmented reality applications that overlay digital content on real-world locations. All of these either became possible or became dramatically better on that single day in May of 2000. Before we leave the history, there is one person whose contribution deserves its own telling, because it is different in kind from the work of Parkinson and Easton and Getting, and because it was overlooked for decades. Gladys West was a mathematician who was hired in 1956 at the Naval Surface Warfare Center in Dahlgren, Virginia. She was the second African-American woman ever hired as a professional at the facility. She would spend the next 42 years there. West's work focused on satellite geodesy, the science of measuring the Earth's shape and gravitational field from orbit. Using data collected by satellite altimetry missions, she programmed increasingly precise mathematical models of the Earth's surface on the computers available to her, beginning with the IBM 7030 Stretch, one of the most powerful computing machines of its era. Her task was to process vast amounts of satellite data and produce models of the geoid, the mathematical surface that represents what mean sea level would be if the oceans covered the entire Earth and were influenced only by gravity and the Earth's rotation. The geoid matters for GPS because the Earth is not a perfect sphere. It is not even a perfect ellipsoid. The Earth's mass is distributed unevenly. Dense rock formations pull the gravitational field stronger in some places. Lighter sediments leave it weaker in others. The planet is wider at the equator than at the poles. Mountain ranges and ocean trenches create local variations. All of these irregularities affect the geoid, creating a lumpy, undulating surface that deviates from a simple mathematical shape by tens of meters in places. GPS calculates positions in a mathematical reference frame based on an idealized model of the Earth. Converting those positions into the latitude, longitude, and altitude that appear on your map requires knowing the relationship between the mathematical reference frame and the actual shape of the planet. Without an accurate geoid model, the translation introduces errors that no amount of clock precision or atmospheric correction can fix. A GPS position calculated against the wrong model of the Earth is accurate in the mathematical sense, but wrong in the practical sense, placing your dot in the wrong place relative to the terrain, the buildings, and the roads. West's geodetic models, developed over decades of painstaking computation, contributed to the increasingly precise representations of the Earth's shape that the GPS system uses. The current standard reference frame for GPS, called the World Geodetic System 1984, or WGS-84, defines the coordinate system that all GPS positions are expressed in. It incorporates detailed models of the geoid that draw on the kind of satellite geodetic work that West and her colleagues performed. For decades, West's contributions were largely unknown outside the small community of geodesists who used her work. Recognition came much later. She was inducted into the Air Force Space and Missile Pioneers Hall of Fame in 2018, at the age of 87. She died on January 17, 2026, at the age of 95. West worked in an era when the computing itself was laborious. The programs she wrote had to account for tidal forces, atmospheric drag on the satellites, and the gravitational influence of the sun and moon on the satellite orbits, all while running on machines that had a fraction of the processing power of a modern smartphone. The iterative refinement of these models, running the data, checking the results against observations, adjusting the parameters, and running again, was the kind of work that required both mathematical sophistication and extraordinary patience. It was not glamorous, and it did not produce dramatic breakthroughs that made headlines. It produced incremental improvements in accuracy, fractions of a meter at a time, accumulated over years and decades. Her story matters not only for what she contributed, but for what it reveals about how systems like GPS are actually built. The public narrative tends to focus on satellites and signals and presidential announcements, but the system also depends on decades of quiet mathematical work, performed by people whose names rarely appear in the popular histories, that makes the physics meaningful in the real world. Without the geoid models, the satellites would broadcast precise time to receivers that couldn't translate it into a position on any actual map. Now let's return to the signal and look at something we glossed over earlier, because it reveals both how the system works day to day and how it can fail. We said earlier that the navigation message is broadcast at 50 bits per second and takes 12.5 minutes to transmit completely. This extremely low data rate is a consequence of the signal's weakness. The slower the data rate, the more signal energy can be accumulated per bit, and the more reliably each bit can be decoded. At 50 bits per second, each bit lasts 20 milliseconds, and the receiver integrates the incoming energy over that entire interval to determine whether the bit is a 1 or a 0. The trade-off is speed versus reliability, and for a signal that arrives 1,000 times weaker than the noise, reliability wins. The navigation message is organized into a hierarchy of frames, subframes, and pages. Each subframe is 10 words long and takes 6 seconds to transmit. 5 subframes make a frame, which takes 30 seconds. Subframes 1 through 3 contain the satellite's clock correction data and its precise ephemeris, and they repeat in every frame. Subframes 4 and 5 contain the almanac and other supporting data, and they cycle through 25 pages, so the complete almanac takes 25 frames, or 12.5 minutes, to transmit. This structure means that when your phone first turns on and has no prior knowledge of the satellite constellation, it takes a while to collect enough information to compute its first fix. This is called a cold start. During a cold start, the receiver has to search across all possible satellite codes and all possible time offsets to find the signals, then wait for the navigation data to arrive. A cold start can take 30 seconds or more, sometimes over a minute. In practice, most phones avoid full cold starts through a technique called assisted GPS, or AGPS. The phone uses its cellular or Wi-Fi connection to download satellite almanac data, approximate ephemeris, and a rough estimate of its own position from an assistance server maintained by the phone manufacturer or the GPS chip vendor. With this information, the phone knows approximately where to look in the sky for each satellite, approximately what time it is, and approximately what Doppler shift to expect on each signal. This narrows the search dramatically and allows the receiver to lock onto satellites and compute a fix within a few seconds. The assistance server is a quietly essential piece of the modern GPS experience. Companies like Apple, Google, and Qualcomm maintain vast databases of satellite ephemeris predictions, computed from the same orbit data that the ground control segment uses, but extended further into the future using orbital models. When your phone contacts these servers, it downloads predicted ephemeris data that is valid for hours or even days, along with an approximate position derived from the cell tower or Wi-Fi network your phone is connected to. This combination of approximate position and predicted satellite data is sometimes called long-term orbit information, and it allows your phone to skip the laborious sky search and jump directly to tracking the satellites that should be visible from your current location. This is why your phone sometimes takes a moment to find your location when you first open a map application, but subsequent fixes come almost instantly. If the phone has recent GPS data cached, the next fix is nearly instantaneous. If the phone has been off for days or has moved to a different continent, the cached data is stale and a fresh cold start or an assisted start is needed. There is another subtlety in the navigation message worth understanding. The almanac data, the approximate orbital information for every satellite in the constellation, serves an important purpose beyond initial acquisition. It allows the receiver to predict which satellites will rise above the horizon in the coming hours and which will set. This prediction enables the receiver to prepare for satellite transitions, smoothly incorporating new satellites into its solution as they become visible and dropping old ones as they sink below the horizon. Without the almanac, the receiver would have to search blindly for new satellites, wasting time and power scanning codes against a sky full of noise. The almanac also enables a feature that many users experience without realizing it. When you travel to a completely different part of the world, your phone's GPS may take slightly longer to get its first fix, because the almanac and cached ephemeris from your home location don't match the satellites visible at your new location. The phone has to acquire new satellites, download their ephemeris, and build a fresh constellation picture. Assisted GPS mitigates this, but without an internet connection, the delay is noticeable. This is one of those moments when the invisible infrastructure briefly becomes visible in the form of a spinning location indicator that takes a bit longer than usual. The signal structure also reveals something about the system's military origins. In addition to the civilian signals on L1 and other frequencies, each GPS satellite broadcasts a separate military signal using an encrypted pseudo-random code called the PY code. This code is much longer and more complex than the civilian coarse acquisition code, chipping at 10.23 million chips per second, 10 times faster than the civilian code. The faster chip rate gives the military signal better precision and better resistance to interference. The encryption means that only receivers with the correct cryptographic keys can process the signal. There is a newer military signal called M code, which was introduced with the Block 2 RM satellites and expanded in subsequent generations. M code is designed to be more resistant to jamming than the PY code. It uses a different modulation technique that places more signal power at the edges of the frequency band, creating a split spectrum shape that allows directional antennas to focus the signal in specific areas. This means the military can, in theory, increase the effective signal power in a theater of operations by aiming the satellite's M-code transmission at a specific region of the Earth's surface, making it much harder for an adversary to jam. The technology is called spot beaming, and it represents a significant evolution in the military's ability to ensure GPS availability in contested environments. This dual signal architecture reflects the fundamental tension in GPS's history. The system was designed and funded by the military, for military purposes, with military money. Its extraordinary value as a civilian technology was recognized and embraced, but the military has always maintained a separate, more capable tier of service for its own operations. The civilian signal is open and free. The military signal is encrypted and restricted. They coexist on the same satellites, broadcast through the same antennas, governed by the same atomic clocks. And the vulnerability of the civilian signal brings us to one of the most important aspects of GPS that most people never think about. We established earlier that the GPS signal arrives at your phone at roughly -130 decibels relative to a milliwatt. That is extraordinarily weak. The satellites are 20,000 kilometers away. Their transmitters output only a few tens of watts, and the signal spreads over a huge area of the Earth's surface. By the time it reaches you, it is barely detectable. This means that GPS is surprisingly easy to disrupt. A transmitter broadcasting noise or a false signal on the GPS frequencies doesn't need to be powerful. It just needs to be stronger than the genuine satellite signal at the receiver's location, and the genuine signal is already 1,000 times weaker than the thermal noise floor. A 1-watt jammer, a device that could run on a battery and fit in a shirt pocket, can deny GPS reception across a radius of roughly 100 kilometers in some conditions. Higher power jammers extend that radius further. This is not a theoretical concern. GPS jamming is a real and growing problem. Small personal jammers are commercially available online in many countries. Truck drivers buy them to prevent their employers' fleet tracking systems from monitoring their movements. They plug the jammer into the cigarette lighter, and it broadcasts noise on the GPS frequencies, blinding any GPS receiver within range. These devices are illegal in the United States and most other countries, but they are cheap, widely available, and effectively unenforceable. The effects of personal GPS jammers extend well beyond the vehicle carrying them. A trucker driving past a hospital may not know that the hospital uses GPS timing to synchronize its record systems. A jammer on a vehicle passing through an airport perimeter road has disrupted airport GPS-based landing systems. There have been documented cases where a single personal jammer caused GPS outages, affecting emergency services, cellular networks, and aviation navigation. Jamming is disruptive but detectable. A receiver that's being jammed knows it's not working. The noise overwhelms the signal, and the receiver either produces no fix or reports that its fix is unreliable. The receiver can warn the user that something is wrong. The more insidious threat is spoofing. A spoofer broadcasts fake GPS signals that mimic the structure and coding of the real signals but carry incorrect timing and position information. A well-designed spoofer can gradually shift a receiver's calculated position without triggering any alarms. The receiver still produces fixes. The fixes still look normal, but they point to the wrong location. The user has no way to tell from the GPS data alone that anything is wrong. The technical requirements for building a convincing spoofer have dropped steadily as software-defined radio hardware has become cheap and powerful. A software-defined radio can generate arbitrary radio signals under software control, and open-source GPS signal simulators exist that can produce realistic GPS signals in real time. These tools were developed for legitimate purposes, testing GPS receivers in laboratories without needing to wait for actual satellites. But the same capability that lets an engineer test a receiver in a lab lets a bad actor fool a receiver in the field. Spoofing attacks have been demonstrated by academic researchers, and they have been observed in the field. Ships in the Black Sea have reported their GPS systems showing them miles from their actual positions. Aircraft in certain regions near conflict zones have reported GPS anomalies consistent with spoofing. The military GPS signal, with its encrypted codes, is much harder to spoof because the attacker would need to know the classified encryption keys to generate a convincing fake signal. The civilian signal, with its publicly documented codes and freely available specifications, is inherently more vulnerable. The vulnerability of GPS is not limited to navigation. GPS timing is woven into the infrastructure of modern life in ways that most people never encounter directly. Cellular networks use GPS to synchronize their base stations, coordinating the timing of transmissions and handoffs between towers. Power grids use GPS timing to synchronize phasor measurement units that monitor the health of the electrical grid. Financial trading platforms use GPS timestamps to establish the precise ordering of transactions when trades execute within microseconds of each other. Air traffic control systems, maritime shipping, emergency response dispatching, railroad switching, scientific instruments that measure earthquakes and atmospheric phenomena, all of them depend on GPS timing that could be disrupted by a device small enough to carry in a backpack. The sheer ubiquity of this dependency has led security researchers, government agencies, and engineering organizations to study the implications of a widespread GPS disruption. The conclusions have been consistent. Modern societies are more dependent on satellite navigation and timing than most of their institutions realize, and backup systems are inadequate for the scale of that dependency. A sustained regional GPS outage, whether from a natural event like a severe solar storm or from deliberate interference, would produce cascading effects across telecommunications, energy, finance, and transportation that would be difficult to predict and slow to resolve. The dependency is not abstract. In June of 2019, when the Galileo constellation experienced a ground infrastructure failure that took all of its satellites offline for nearly a week, the disruption rippled through industries that had integrated Galileo timing into their operations. More dramatically, severe solar storms have the potential to disrupt all satellite signals simultaneously. The Carrington event of 1859, the most powerful geomagnetic storm in recorded history, occurred before the age of satellites, but a storm of similar magnitude today would bathe the GPS constellation in high-energy particles, potentially damaging electronics, disrupting signal propagation through a violently disturbed ionosphere, and degrading or denying GPS service globally for hours or days. Some backup and complementary technologies are being developed. Russia operates its own global navigation satellite system called GLONASS, which uses a different constellation and different signal structures. The European Union operates Galileo. China operates Beidou. Japan operates a regional augmentation system called the Quasi-Zenith Satellite System. Each of these systems works on principles similar to GPS and can be used independently or in combination with GPS. Modern high-end receivers can track signals from multiple constellations simultaneously, improving both accuracy and resilience. If the GPS satellites were suddenly unavailable, a multi-constellation receiver could continue to function using the remaining systems. Each of these alternative constellations has its own characteristics. GLONASS uses a different signal multiplexing technique. Instead of giving each satellite a unique code on the same frequency, GLONASS gives each satellite its own slightly different frequency. This approach, called frequency division multiple access, avoids the code interference problem, but uses more radio spectrum. Galileo, the European system, was designed from the start for civilian use and offers an encrypted signal called the Public Regulated Service for governmental users. Beidou, the Chinese system, began as a regional system covering the Asia-Pacific region and was expanded to global coverage. It uses a mixture of geostationary, inclined geosynchronous, and medium Earth orbit satellites, a more complex architecture than GPS's uniform medium Earth orbit constellation. A receiver that tracks all 4 constellations simultaneously can see 40 or more satellites at any given time, providing exceptional geometry and redundancy. If one constellation degrades, the others continue to provide coverage. The main limitation is that each constellation uses its own reference frame and time system, so the receiver must maintain separate models for each and combine them carefully. Modern multi-constellation receivers handle this automatically, and the result is a level of positioning resilience that no single constellation can match. On the ground, some organizations are deploying enhanced LoRaWAN, a modernized version of the radio navigation system that predated GPS. LoRaWAN uses powerful terrestrial transmitters, broadcasting low-frequency signals that are much harder to jam than satellite signals because they are thousands of times stronger. Fiber optic time distribution, where precise timing is delivered over existing telecommunications fiber rather than through space, is another backup being explored. And chip-scale atomic clocks, miniaturized atomic timekeeping devices small enough to be built into infrastructure equipment, could provide holdover timing that keeps systems running for hours or days if the GPS signal is temporarily lost. Inertial navigation systems, like the ones that failed Flight 007, have also advanced dramatically since the 1980s. Modern inertial measurement units use micro-electromechanical systems, tiny silicon accelerometers, and gyroscopes etched onto chips. These are the same sensors in your phone that detect when you rotate the screen from portrait to landscape. They are not accurate enough on their own for long-term navigation, but they excel at measuring short-term changes in motion. When fused with GPS, they fill in the gaps between satellite fixes and provide instantaneous response to movement that GPS, with its update rate of a few times per second, might miss. Some high-end navigation systems fuse inertial data with GPS so tightly that the result is smoother and more accurate than either system alone. None of these backups match GPS in universality, precision, and cost. The constellation orbiting overhead remains the primary source of position and time for billions of devices and thousands of systems. For now, the system works, and the satellites keep orbiting. Let's bring the full chain back together now, because we've followed each piece separately, and it helps to see them working in sequence, from satellite to screen. You open a map on your phone. The GPS chip powers up and begins scanning. It knows roughly where to look because it has cached almanac data from its last fix, and it downloaded fresh assistance data from a server through the cellular network when you turned the phone on. Within a few seconds, it has locked onto signals from 8 satellites distributed across the sky. For each satellite, the chip generates a local copy of that satellite's unique pseudo-random noise code and correlates it against the incoming radio energy, searching for the match that indicates the signal has been found. When it finds the match, it reads the timestamp and the ephemeris data from the navigation message. For each satellite, it calculates a pseudorange by subtracting the satellite's reported transmission time from the chip's own clock reading at the moment of reception and multiplying by the speed of light. These pseudoranges are contaminated by the chip's own clock error, by ionospheric and tropospheric delays, by multipath reflections from nearby buildings, and by the inherent noise of the receiver's electronics. But the chip has more equations than unknowns. 8 satellites give it 8 equations for 4 unknowns. It sets up the system, solves it iteratively, and converges on a 3-dimensional position and a clock correction. The clock correction is applied, synchronizing the chip's cheap quartz oscillator to the atomic clocks in orbit. The ionospheric delay is estimated, either through the Klobuchar model if the chip has only a single frequency, or by comparing delays across L1 and L5 if it tracks both. The tropospheric delay is estimated from an atmospheric model. If WAS corrections are available, they are applied, refining the ionospheric, orbital, and clock error estimates. The relativistic corrections are already baked into the satellite clock frequencies before launch, so the chip doesn't need to compute them separately. The result is a latitude, a longitude, and an altitude, expressed in the WGS-84 coordinate system that the satellites use. The chip also computes a confidence estimate, the horizontal accuracy in meters, which it reports alongside the position. Your phone's mapping software takes those coordinates, transforms them onto the map projection, places the blue dot, and updates it as new fixes arrive. The whole process repeats several times per second. Each fix is independent. Each one is a fresh solution to the same geometry problem, drawing on atomic clocks, orbital mechanics, the speed of light, the shape of the Earth as modeled by decades of geodetic work, the state of the ionosphere at this moment, and corrections for the curvature of space-time predicted by a theory published in 1915. Your phone doesn't use GPS alone, though. It fuses the satellite fix with other position estimates to produce the most accurate result it can. Wi-Fi positioning uses the known locations of nearby wireless access points, catalogued by vehicles and devices that previously visited the area while GPS was active, to estimate position even when satellite signals are weak or unavailable. Cellular positioning uses the known locations of nearby cell towers and the signal characteristics to produce a rougher estimate. The phone's inertial sensors, its accelerometer, and gyroscope track movement relative to the last known position, providing continuity when satellite signals drop out temporarily. A barometer estimates altitude changes. Bluetooth beacons in indoor spaces provide location references where no satellite signal can reach. The Kalman filter deserves a moment of its own, because it is one of the most important algorithms in the history of engineering, and it runs quietly inside your phone every time you move. Rudolf Kalman published the filter in 1960, the same year that the Transit Navigation satellite was launched. The filter is a mathematical procedure for combining noisy, uncertain measurements into the best possible estimate of a system's true state. It works recursively. At each time step, it uses the system's known dynamics to predict what the state should be, then compares that prediction against the new measurement and computes an optimal blend of the two. If the prediction is highly certain and the measurement is noisy, the filter mostly trusts the prediction. If the measurement is precise and the prediction is uncertain, the filter shifts toward the measurement. The weighting is not fixed. It adapts at every step, based on the estimated uncertainties of both the prediction and the measurement. In GPS, the filter tracks not just your position, but also your velocity, the receiver clock error, the rate at which the clock error is changing, and sometimes additional states like atmospheric delay estimates. Each new GPS fix is treated as a measurement, fed into the filter alongside predictions based on your last known position and velocity. The filter produces a smoothed position estimate that is more accurate and more stable than any single GPS fix alone. All of these inputs feed into a sensor fusion algorithm, typically a variant of the Kalman filter, that combines them according to their estimated reliability at each moment. Under open sky with good satellite visibility, GPS dominates. Inside a building, the algorithm shifts to Wi-Fi and inertial data. Underground or in a deep urban canyon, it falls back to whatever signals are available, cellular positioning and dead reckoning, and anything else it can find. The Kalman filter was originally developed for aerospace navigation, and Rudolf Kalman's paper was, at first, largely ignored by the statistical community because it was published in an engineering journal rather than a statistics journal. But NASA quickly recognized its value and used it in the guidance systems for the Apollo program. The same mathematical framework that helped guide astronauts to the moon now guides your phone through a shopping mall. The filter is so fundamental to modern navigation and control that it's been called one of the greatest discoveries in applied mathematics of the 20th century. This fusion is why your blue dot sometimes seems to know where you are, even in places where GPS shouldn't work. The dot isn't tracking you through the ceiling of the subway station. Your phone is using every available signal to maintain an estimate, bridging the gap until you emerge and the satellites take over again. There are a few more dimensions of GPS worth spending time with, because they reveal how deeply the system has embedded itself in the infrastructure of civilization. GPS time is its own timescale. It was set to match Coordinated Universal Time on January 6, 1980, the epoch from which GPS time counts forward as a continuous count of weeks and seconds. Since that date, Coordinated Universal Time has been adjusted by the periodic addition of leap seconds, corrections needed because the Earth's rotation is gradually and irregularly slowing due to tidal friction. GPS time does not add leap seconds. It runs continuously, counting every second without interruption. As the leap seconds accumulate, GPS time drifts ahead of Coordinated Universal Time by the number of seconds that have been added since the epoch. The GPS navigation message includes a parameter that tells receivers the current offset between GPS time and Coordinated Universal Time, so receivers can convert between the two. This continuous, unbroken timescale is one of the things that makes GPS time so useful for infrastructure. Systems that need precise timing without the discontinuities introduced by leap seconds prefer GPS time as their reference. When a leap second is added to Coordinated Universal Time, every system that uses it has to handle the insertion, and the history of leap seconds in computing is littered with bugs, crashes, and brief outages caused by software that didn't handle the extra second correctly. GPS time avoids the problem entirely by never having leap seconds. The timing precision that GPS distributes has become the heartbeat of several critical systems. Cellular base stations use GPS receivers to keep their transmission timing synchronized to within tens of nanoseconds. This synchronization is necessary for the handoff of calls between towers, for the coordination of transmissions in time division systems, and for the operation of advanced cellular technologies that require precise timing between base stations. If the GPS timing reference were lost, cellular networks would gradually desynchronize, leading to dropped calls, reduced coverage, and degraded data throughput. Some base stations have holdover oscillators that can maintain timing for a while without GPS, but the holdover degrades over time, and a sustained GPS outage would eventually affect service quality. Power grid operators use GPS timing to synchronize phasor measurement units placed at substations across the grid. These units measure the voltage and current on the grid at the same precise instant, allowing operators to see the state of the entire grid simultaneously, rather than relying on measurements taken at slightly different times. The simultaneous measurement is critical for